That big TV back there, man. He's got luxury. That big screen TV. Very
The
nice.
funny thing is that I don't watch TV.
Oh, yeah. Well, that's good. That means you have a life. All right, here we go. Logarithms. Back to logarithms. You remember, what is a logarithm? The logarithm of a number is the power to which you must raise the base to get that number. So the top one here, this, if you call this question mark, what power b, the base to what power equals 1? Now you remember b, the base has to be positive, and the base cannot be 1. Okay. I'll tell you what. I'll get to that. Let's just hit this one right here. I'm being reminded we may not have finished the slide before. But b to what power is 1? There's only one power you can raise a positive number to and get 1 if the number's not 1. 0. Right? Right? So b, question mark. So this equals 0. All right? Trevor's saying we didn't finish the slide before.
It's like you gotta skip.
Oh, okay, you're right. Okay, look at this. Here. Yes, you're right. Thank you. Yeah, we got this little log table on the right. And here we have log of 7 divided by 2. We're going to use the properties of logarithms, right? So this equals the log of 7. If you go back a couple slides, it says the log of a quotient is the difference of the logs. So this equals log 7 minus log 2, which from our chart over here on the right, the log of 7 is 0.8451 minus the log of 2, 0.3010 equals 54.5441. Right? Okay, subtract the logs. The log of 100. Well, you might be able to do this one in your head, actually. Because if we call this question mark, what's the base here? 10 to question mark equals 100. Well, question mark equals 2. Okay? That's one way to do it. Another way to do it is this, is to say that log 100, log of 100 is log of 10 squared. And you can bring this down front. So that equals 2 log 10. And you see from the chart on the right that the log of 10 is 1, which makes sense. That's the power you have to raise 10 to get 10. You remember, log without a base, log without a base is log base 10. So this equals 2 times 1 is 2. So either way. Ooh.
Mr. Miller?
Yeah.
So you're saying that the log without base is a log of 10, but do you know that if I say only LG, it's the same thing, or you guys?
LN.
Oh.
Like LN of x is log base e of x. So LN, that is called natural log, is log base e, except that we never write it that way. But LOG of x is log base 10 of x. But we never write it that way. But if it will help you, by all means, you're allowed to write in base 10 here if you want. If that will help you. I won't take, I don't take points off of that. However you do the problem, I'm good. If it doesn't involve your neighbor. Down here. Oh, we're getting good. This is good. Okay, you ready? Log square root of 7. Square root of 7 is not on our table. I wouldn't expect it to be on the table. This is log 7 to the 1/2 power. And then that exponent can come down front. So this equals 1/2 log of 7 and that's 1/2 0.8451. Well, that's not going to come out even, is it? That's going to be 4.42255. Now, all of these you're doing just off that table. The purpose of this slide is to familiarize you a little bit with the properties of logarithms, that the log of a product is the sum of the logs, the log of a quotient is the difference of the logs, etc. This one, okay. Log 27/16. All right. By the way, you can check some of your answers on your calculator if you wanted to. Right. For example, just for a quick one. Clear. Log square root 7. It's pretty close. 4.22549. Not bad. So, over here. How about this one here? Log 27/16, that's log 27 minus log 16. 27 and 16 are not on our little table, but these are even powers of 3 and 2. So these equal log 3 to the 3 minus log 4 to the, no, not 4. That would be true, but log 2 to the 4. Now these exponents can come down front. So that's going to be 3 log 3 minus 4 log 2. And from our table, that's 3 log, not log. Log of 3 is 4.477. 3 times 0.4771 minus 4 times 0.9 3010. And as you see from that calculation, that is 0.2273.
Mr. Miller?
Yeah.
So if I do this in my calculator, that's not enough work?
If I let you use your calculator, this could be on the non-calculator part. Maybe I just give you that chart up there. So it could be, you should know how to do this on your calculator. I agree with you. It'd be a lot nicer if your Big Bean teacher would let you, right? All right. Skip that one. Let's get back to where I started by mistake today. Log BB. That's the power I have to raise B2 to get B. So I call this a question mark. This means that B to the question mark equals B to the 1, right? Equal bases. So question mark equals 1. So just get used to saying log base B of something is the power to which B must be raised to get something. All right?
No solution.
Oh, why do you say that?
Because everything raised to the 0 power is 1. So that cannot be a 0.
So he said, okay, this means that B to the question mark equals 0. And he's saying since B up here, since B is positive not equal to 1, how do you raise a non-zero number to any power and get 0? The only way you can raise a number to a power and get 0 is if the number is 0. But up here, B can't be 0 because it's a base of a logarithm. So he is absolutely correct. No solution. Now I want to show you something else. I think we did the graphs of these. I believe we did, yes. We did the graph of this is f of x equals log base b of x, and it's that shape if b is bigger than 1, and it's this shape if b is between 0 and 1. And in either case, the first case you have a vertical asymptote to negative x-axis. The second case, you have a vertical asymptote to positive x-axis. Or did I say x-axis? Y-axis. So if you know the graphs, they can help you out here. Because the log of 1, that's this point right here. Log of 1, y-coordinate 0. So that gives you the first one. Well, the second one, not so much. It says the log base b is going to be 1. So if I go out here to b, up here is the point b comma 1. And then log 0, you see that the logarithm is not defined for 0, which is the x-axis or y-axis. So this is the x equals 0 is the y-axis, and the log graphs never touch the y-axis. So that's why, that's another reason why the answer to part C is undefined. I'm gonna have to start taking my big water can to work. Drinking too much water. All right. Oh dear. Oh my goodness. What are we doing here? We're going to use the properties of logarithms. Write that mess as a single logarithm. So the first thing I see to do is to write log x plus 2 and take that 2 and put it up there, squared, minus log x. And the difference of logs is the log of the quotient. Good question.
So where is the squared, Mr. Miller?
Yeah, that's what he was asking. There you go. Thank you. How about this next one? Log 2, natural log of 2. 3 natural log x is plus log x cubed minus log 7 cubed minus log 5 squared let's do some combining. This is the log, that the sum of logs is the log of the product. So this is natural log of 2x cubed. How should I write that? I'm going to write that this way. Watch. Minus that product. That's natural log of 7 cubed times 5 squared. And that's going to be natural log 2x cubed minus 7 cubed 5 squared.
So when it asks about write it to a single logarithm, then you don't have to solve anything?
No,
Just
simplify. Yep. Nothing to solve, really. This one takes a little bit of work, but the point here is to see if someone understands what logarithms are. This one takes a little bit, when I say a little bit of work, it takes thought. Question. It says to write on the same graphs here, e to the x and 10 to the x. Right? E to the x and 10. You know what? Maybe I did not have the, I don't know, this, when I put the log graphs up on the right, maybe we haven't had that. Maybe we're coming to it. I know we have it in my other class. See, it's another place where we just passed logarithms in my other college algebra class, and I forget what we've done in each class. So e to the x, what does it look like? Something like that, roughly. F of x is e to the x Now, pop quiz. Here's a pop quiz. In the next few seconds, I'll tell you what, we're going to do the Jeopardy jingle. Right on this graph, this. How does that function go on that graph, on the left graph? All right, here. Do a little jingle here.
Sometimes you need to get away from the kids for grown-up time.
Oh,
Or get away from the grown-ups for kid time.
ready? How would 10 to the x go on there? Ten to the x for positive numbers would grow faster than e to the x. So on this, the right side, 10 to the x is going to grow much faster. But 1 over 10, like 10 to the minus x is 1 over 10 to the x. So 10 to the negative 2 is 1 over 10 to the 2. So it's going to also get smaller faster over here. So this is g of x equal 10 to the x. All right. Now we're going to use those, it says, to get the graphs of their inverses. Because exponential functions on the left are inverses of the logarithmic functions on the right. And you know what? We have a typo here. Right here, get rid of this A. Right here, get rid of that A. So delete the A that was over here on the f of x right there, okay? So these two would go here how? The student will recall that inverses, the graphs of inverses are going to be the graphs of the functions reflected about the line y equals x. So I'm going to reflect about that line. Now, this y-intercept at 1 becomes an x-intercept at 1. The asymptote on the negative x-axis becomes an asymptote on the negative y-axis. The red graph here is 10 to the x. It's closest to the asymptote. So over here, the log to the x, log base 10, excuse me, is going to be closer to that asymptote. The blue one over there is e to the x. It is log base e. It's going to be further away. So this is a good mental exercise as to whether, first of all, someone understands the exponential functions, that the higher the base, the faster it's going to grow on the positive side here. And the faster it's going to diminish on the left. So it's going to get smaller quicker on the left for negative values of x. It's going to grow faster for positive values of x. And then we reflect those two about the line y equals x. And without knowing anything about their graphs, we got the graphs because we knew they were the inverses of the exponential functions. And we know that the graphs of inverses are obtained by reflecting about the line y equals x. Sneaky, 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 sneaky. So remember these graphs. The graphs of basic exponential functions on the left, basic log functions on the right. I should say any base with b greater than 1 is going to have that general shape for the log. And this general shape for the exponential. If b were between 0 and 1, remember b can either be bigger than 1 or between 0 and 1. And I'm not going to clutter these graphs, but if they were between 0 and 1, the graph shape would be like that. Oh, except higher. That would be the basic shape of for an exponential function with b between 0 and 1. And over here on the right, that would correspond to a logarithm like that. But I don't want to clutter these graphs any more than they already are. Oh. Whoa. Okay. Question. Let's just go back here a second. These exponential functions on the right, what are their domain and what are their range? I'll give you a clue. They're the same for each one. The domain is every x value you're allowed to plug in. Minus infinity to infinity for the domain. And the range, only positive numbers, not 0, but positive. So 0 to infinity. Something you may or may not have noticed is that over here, they're swapped. The domain over here is only positive numbers. And this is always true for inverse functions. The range and domain flip. The range here is going to be minus infinity, all possible y values, up to positive infinity. All right. Just thought I'd toss that on there. No extra charge. Now, log 2 minus x. I'm going to warn you, this one has a little twist to it. It's a twist we've seen before, though. It's a twist we've seen before. Ready? How do you start all these? With a plan. Question. First step, you pick something from your library of functions. So in our library of functions now is y equals log of x. That's from our library of functions. That is a function whose graph we know. Now we need to turn that in to log 2 minus x. The first step I think most people would get. 2. Y equals log of negative x. You substitute negative x in for x. That is what kind of transformation? Reflection. About y-axis. Here's where people screw up. We need to get 2 minus x. So the next step you see on papers is this. Stick a 2 in it. What kind of transformation is that? Almost guaranteed you'll get it wrong. I would. It is none of our transformations that we know about. That isn't any of the transformations. It's unpredictable. You can't just stick a 2. You got to substitute the whole thing. So this, now let's back up. We have log of negative x. What do I need? Down here, eventually, I need y equals log 2 minus x. That's what I eventually need. So right now, I have y equals log negative of something. I'm going to see the negative stays there. I'm substituting in for x. What do I have to substitute in for x so that when I take the negative of it, I get 2 minus x? That is x minus 2. Whoa, head trip. See, I have that negative there. And that negative is going to flip that x minus 2 to give me a minus x plus 2, which is 2 minus x. And the good part is, when I substitute x minus 2 in for x, that is a transformation. Right 2. So this is shift right 2. So this is the correct step 3.
Mr. Miller,
Yes, sir.
on the step 3, can you do something like minus x plus 2 in the parentheses?
Okay, minus x plus 2, the answer is no. And the reason why is minus x plus 2 log. That would give you log minus x minus 2. When you distribute the negative sign,
I know, but within the parentheses. So the minus is not in front of the small parentheses, it's within the parentheses.
yeah, okay, I see what you're saying, but if you're going to substitute, okay, I think you're saying this. Hold on here. You're saying log minus, like that. Right? The only problem is, what is that? If you didn't substitute in for x, because if you substitute in for x, you would have more parentheses. So what that does, I don't know what that does. You really have done two things there. So see, whatever applies to the x has to apply to the 2 as well. And so if this negative sign here, if that negative sign applies to the x, if you're substituting, it's got to apply to the 2 as well. That would be the best way I could describe it. So you have to take the negative of x minus 2 to get 2 minus x. Now, let's graph. Number 1, we know at the back of our hand. We know this one bad. We're bad. Right? Graph 1. Graph 2, reflect. Graph 3, shift right 2. So I'm going to put graph 3 on the right. So everything goes to the right 2. All my graph's features go to the right 2. So this vertical asymptote goes from the y-axis over here to 2. The x-intercept goes from -1. It goes to the right 2 to +1. Oh no. My board just froze. So this is bad. All right. We're going to take a picture of the screen. Hopefully I got a picture of the screen good. I have to. This would happen with only a couple minutes left. Usually I lose the whole screen when I do that. We'll see. Yeah, okay. This is why I take pictures. All right. Okay, so over on the right now, I have a 1 right here. That's my x-intercept moved over 2. And my final graph looks like this. And what is that going to be? What's that point there? Plug in 0. That's log of 2. Is that point there? You don't have to figure out what that is unless I give you a calculator. And you see down below that little screenshot, the little calculator screen. Why does the graph, the blue graph, why does it quit right there? And the answer is your graph, your calculator only puts 1 point per horizontal pixel. And the graph gets so steep right there, it actually does this. It kind of goes down very steeply. The problem is it goes down like that all in 1 pixel. So it can only put 1 point there, and it can't put points below it on the same pixel. That sounds like an excuse, but that's a limitation of the calculator screen. What's the domain of my final function?
Mr. Miller, just a quick
Yes.
question. So if is it a shift to the right by 2, the last one?
Yeah?
So isn't it like the stuff on the number 3 equals to number 3 instead of the 2?
No, the reason why is that on the left, this is x equals 0 is the vertical asymptote. And when you shift it to the right 2, it's going to be x equal 2, the vertical asymptote.
Okay.
So the domain of that graph on the right, you see the x values that are on that graph are -infinity up to but not including 2. The range stays the same, minus infinity to infinity. And that's going to do us for today. Yeah. Yeah. So now I'm going to save this.
See you, Mr. Miller.
Yeah, I'm going to miss you tonight at Spark. I don't know what to do with Spark without you, Mario, and Diego. Mario and Diego are on the road. Yep. See you, Tomas.
Yeah.
Have fun.
Later, Mr. Miller.
Yeah, take care.